is lecture 4B. And I'll be specifically talking about chapter 4. And we'll be dealing with forces, or Newton's second law, F equals ma, forces in newtons. This is in kilograms, and this is in meters per second squared. And so if you apply a force to something, right? So pulling a box and say a frictionless surface F, and this weighs a certain mass, the acceleration would be force over mass, right? So that'll be in newtons. Now if we have weight, on the other hand, so an object, that's, a certain mass, its weight is the force given by mg, where g is 9.8 meters per second squared. All right, we don't really worry about the sign of it in this case because weight is always pulling down. Force of gravity is always pulling down. So let's look at this as far as comparing, say, Earth and Moon. And we'll get into gravitational forces in chapter 5 in the next lecture. And on Earth, the acceleration of gravity is 9.8 meters per second squared, while on the Moon, the acceleration is 1.67 or so meters per second squared. So it's about 1/6 on the Moon, the acceleration of gravity. That means the weight of, say, 100, say on Earth, we have a mass of 100 kilograms. Its weight will be 100 times 9.8, or 980 newtons. So that's what weigh on the Earth. On the Moon, the mass is still, so if we're on the Moon, the mass is still 100 kilograms, but the weight is this would be 1.8, 1.67, so it would be 167 newtons on the new Moon. So your weight is much less. That's why if you watch the Apollo astronauts, when they were hopping on the Moon, they seemed to actually float at times because the acceleration of gravity is less. It's much easier to spring. Acceleration pulling it down is much less. So mass is still there, makes no difference. That's why to accelerate something depends on the mass of the object. So that's the comparing the Moon and Earth. We'll get into gravitational laws, Newton's law of gravitation in chapter 5. I'll cover that later. So that's just a bit part between those two. All right. All right, so let's move on a little bit here. All right. And you did the Atwood machine for the lab. And an example, the homework problem has one. So let's do a simple, relatively simple case. We have two masses, M1, M2, and this M2 is not necessarily heavier than M1, it's just that's the way of drawing it. And they're overpoised, so they're connected, right? The mass, so we use Newton's F equals ma to do this, to look at this. Now, if you just drop an object, right, take a mass m1 and drop it, the acceleration will be g, which is 9.8 meters per second squared downwards. So I'm not worrying about the sign at the moment. We'll get into that a little bit of detail. So it's just drop it, that's the acceleration. In this case though, you have the balance is weighing out. So let's look at this case of just free fall. So why is it accelerating? The force is mg, it's weight. That's the force pulling it down, m1. And the mass being accelerated is the same as the weight that's pulling it down. So if we cancel out m1, we get the acceleration is g, 9.8 meters per second squared. So for a falling object by itself, that's what we get, neglecting air resistance. Now in this case, all right, the masses are together. So if we have F is M, it'll be M1 plus M2 together, right? The force though is not going to be both them together because this one's pulling this way, that one's pulling that way. So the masses are going to cancel out. Or not cancel, or they're going to negate each other to some extent. So in this case, to make it simpler, so I have a positive, I want to make this say 3 kilograms, and this one is 2 kilograms. All right, what would be the acceleration? In this case, it would be 3 minus 2 equals 3 plus 2 times A. Oh, times g, I forget, because the weight is still mg. The force pulling is mg, but they're canceling out each other. Times 9.8. That would be 1 over 5, because this would be 1, this would be 3, plus 2 is 5, times 9.8 is A, is approximately 2 meters per second squared. So it's 1/5 because they cancel out. Now if M2 was bigger than M1, so this was that one and that one, it would still be the same acceleration, but instead of pulling that way, we just pull that way. And likewise, if both M1 and M2 are equal, then the net acceleration is 0, and it's just going to either sit there or move at a constant velocity. So this is the expression for the Atwood machine, is this one here. All right. So for any problem solving the Atwood machine, that's what, and this is G. And it doesn't matter whether one is larger than the other because we're only looking at the size of the acceleration. All right. So that's the Atwood machine as far as that's concerned. This is one of the questions Einstein had dealt with, and art is not my thing. But if you're in a closed elevator, when you get in, the door closes, you just sit there. All right? So, how do you realize you are moving suddenly? Well, you either get pulled upwards, so you feel going down, or you start falling and you start feeling slightly lighter. So in the process, for the beginning part, as you rise, you will first undergo an acceleration upwards. Then, as the elevator travels, acceleration will be 0 because you don't accelerate forever. You start going constant, so you lose that feeling of being pulled down. And then, when you reach the floor you want to get to, right, acceleration is downward because it's slowing you down. So you feel less weight here. Normal here. And heavier here. And we're not going to get into relativity, but this is one of the things Einstein realizes: you can't tell the difference between acceleration and gravity. It's how you can simulate gravity in space is by acceleration. either by accelerating or by moving in a circle, and we might as well go through that again. Again, centripetal acceleration is v squared over r. So if you're moving in a circle, traveling in a circle, again with some radius r and some speed v, you will feel a simulated force pulling you outwards, and this could be enough that you could have gravity in space. This is how they would simulate gravity in space, is by having a rotating capsule. If you've ever seen movies such as 2001, Space Odyssey, I can't think what else. Anyway, movies do that. That's the only way you can simulate gravity, is by simulating rotation. So how does this work here? Okay, how can we determine what would we do? So let's look at an example here, right? So if we are rising, let's say you have a mass of 100 kilograms, right? Your weight, let's say on a scale, would be 980 newtons, because your weight is m times g, right? So when, let's say the elevator accelerates upwards at 2 meters per second squared, here it's a is 0, and then it slows down, a is minus 2 meters per second squared. Because you're moving that way, but the acceleration is that way to slow you down. All right, what would your weight be in each of these cases on the scale? Well, here it's going to be more, here it's going to be normal, and here it's going to be less. So how do we do that? How would we actually look at your weight then? Your force, let's say, force then would be your mass times g plus a, or g minus a, I should say. I want to get it right. Where g is minus 9.8 meters per second squared. Oh, never mind. That should be plus. Let's use that as plus. That's minus. If we're going upwards, then this would be, force would be mg plus 0. And here force, the weight would be mg minus a. Well, in this case, your weight would be 100 times 9.8 plus 2, which would be 1180 newtons. Here you would be 100 times 9.8 minus 2, which would be equal to 780 newtons. All right? So anytime you have that, this is basically how I would suggest doing it, is you can have both a minus, both of them plus, but when you are accelerating upwards, right? Accelerating upwards, you are adding to gravity. So you're going to add them together. So in this case, I'm adding it up. If you are, and this would be the same thing going downwards, right? If you're going downwards in an elevator, what do you feel at first? You're going to be feeling like you're being lighter, because all of a sudden you start accelerating downwards, you feel normal, and then it starts going the opposite direction. So if you use this where g is positive 9.8 meters per second squared, you use up, a is positive going up, negative going down, then this will work, solve any situation, whether elevator starts at the top and starts coming down, or at the bottom and starts going up. All right? So there's a couple of examples of that as far as that is concerned. So every elevator has this situation. You have to accelerate, you suddenly lose that acceleration, go constant velocity, and then you slow down, and that's where you feel there. Okay? All right. So use these expressions. That's how I would suggest doing it as far as that's concerned. So this would be in an elevator. Okay. All right, last thing I want to do for chapter 4 is getting a little bit into friction. And I will show this from the text. And this has terms we call coefficient of friction. This is section 4.8 in the text. And what they talk about there is what we call static friction and kinetic friction. And we're not going to, if I have a situation where I'm actually having to solve a problem, I will provide the numbers for you. So, in this case, where do we want friction? All right, where do we have friction? Friction's always everywhere. All right, if I push something, all right, let's say I got a heavy box and I push it with a force, all right, some force pushing on it, then what you're going to notice, if you ever have a heavy box or something, is when you first, the hardest time to push it is when it's stopped. Then once it starts to slide, it will be easier to push. All right? This, when it's stopped, and push it before it starts moving is what we call static friction. When it starts moving and it starts to slide, we use a term, and this is a Greek letter U, kinetic friction. So, and what the relationship, so friction is based on, so frictional force, which is always opposing the motion. You apply it this way, frictional force is going that way. Then this would be, frictional force is given by mu times g, the weight. And this number ranges basically from 0 to 1, where 0 is no friction at all, and 1 is friction equal to weight. All right, and this would be like the case of a block. If the frictional force is 1, it would be take the same amount of force to lift it up, it would be to slide it across. So this is what we have here. And relating these two, because this force of moving it while it's stopped, and then once it starts moving is less, static friction is always greater than kinetic friction. So that's the case there. So let's do one example with this. Say I have a box, that weighs 1,000 newtons. So Fg, 1,000 newtons. All right, and that's a lot. It's about 100 kilograms of force. And say the mu static is 0.5, and mu kinetic, depending on the surface, 0.3, which is not unusual. If you look in the book, wood on wood, is something like this. All right, what would that mean then? This is static, this is kinetic. All right, if I have a 100 kilogram box or block of wood, all right, what force would it take to push it? The force, because frictional force is always overcoming it. To get the block to move, the force would be mu Ks times 1,000, which would be 0.5 times 1,000 would be 500 newtons. That's the amount of force it would take it to get moving. Right? Anything applied less than that, it's not going to go anywhere, because frictional force will always overcome anything smaller than that. So nothing's going to happen. It's not going to move until you exceed that. You push it, let's say you give it 600, you start slide, whatever. You're right at the limit, it'll start to slide. Once it starts to slide, the force needed is mu K times 1,000 newtons, because it still weighs 1,000 newtons, times 0.3 would be 300 newtons. So that would be the case there of sliding a block. It takes 500 newtons to get it going. Once you get it going, it takes 300 to keep it sliding. That's why you want to keep it sliding as you go along. All right, so that's the case there. Again, friction is given by this, where this is the weight, that's the coefficient of friction, and that's the frictional force opposing that, and mu static is always greater than mu kinetic. So that's one example there. All right, another example, and again, if I give you a case, I'll always provide, this coefficient of static friction or kinetic friction for you in the problem. Because these can only be measured. All right, here's a case. All right, you are driving along and you make a sharp turn. You make a turn and the road is dry. Okay, so like so what? And when it's dry, okay, mu static is approximately 1, and mu kinetic is about 0.8. Now, if it's wet, well, if it's wet, or let's move. Yeah, if it's wet, then this will be about 0.6. And this can be about 0.4, or let's say 0.3. All right? I mean, it depends how wet. It could be really soaking. And R is, say, 100 meters. So you try to move into a turn of a circle of 100 meters, and you have a speed, velocity of 30 meters per second. All right, which is about 65 miles per hour. To make it into a turn, all right, what happens under these conditions? All right, so what you have here in this case, when you're making the turn, is you have frictional force pulling you in, which is given by mu mg, that's a mu, and you have centripetal force, trying to pull, I wouldn't say pull you out, but trying to have you go straight is the thing, and this is given by mv squared over r. So you stay on the road as long as the frictional force, so stay on road, if frictional force is greater than or equal to centripetal force. All right? So as long as you're going slow enough, or have enough speed, I wouldn't say slow enough, speed so that this force pulling you inwards, not literally pulling you in, but it's overcoming, it's enough to overcome the centripetal force pointed out. So if we look at this, mu mg is greater or equal to mv squared over r. One thing about this, and there's always a question there, is you notice the m's cancel out. So it turns out that this limit has nothing to do with the mass of the car. It has to do with the quality of tires, but two cars, light and heavy, if they have the same type of tires, the situation is a little different. I think sometimes people, SUVs and big trucks, they feel like they're so heavy and they're not going to go anywhere, but they're just as likely to go off a road if they're going too fast for conditions than a small Prius like my car. So this would be the condition here. So the mass makes no difference. So what we're going to have here is mu g is greater than v squared over r. Right? So I'm going to try and do these examples here. All right? So for the first one, and I'm going to use g is 10 meters per second squared for just simplicity for this problem. So in the first case, 1, this would be 1 times 10, and comparing that v squared over r, which is 30 squared over 10, that's 1, that would be then this is 10, comparing that to 900 over 10, 100, I'm sorry, r is 100, 9 over 100, this is 9, stay on road. All right, this works. Okay, so that's our speed in all cases. The centripetal acceleration is always going to be 9 meters per second squared, 9 meters per second squared for centripetal acceleration. So as long as this side is square and that side, you're fine. Because regardless of the road conditions, if you're going 65 miles per hour in a turn of this radius, that's the centripetal acceleration trying to pull you out. All right, let's look at the next case then of connector. So let's say, well, in that case, you're going to make it. All right, you're not going to make a problem at all because your centripetal is dry. You're not going to exceed this, so you'll stay on the road. Now, let's say we have this case where it's wet. In this case, we have mu s is 0.6. So we have 0.6 times 10 meters per second squared, which is 6. That's the frictional force. Frictional acceleration, I would say, we can add it times the car. And we compare that to our 900 or 100, which is 9. This is not greater than that. The car will slide. All right? Once it starts to slide, then what you're going to have is kinetic friction, and in that case, mu k is 0.3, and that's going to be 0.3 times 10, which is 3. which is certainly not less than 9 meters per second squared. So you're going to slide. All right. Let's say you got this wet case. All right. How slow do you actually need to travel to actually make it? All right. What we'd have to do then in that case is, let's go back to here. Let me leave that up a minute. All right. Okay, let's just review this a little bit. This is dry conditions, wet conditions. If you're going 65 miles per hour on a wet road with this radius, you're going to slide off. And because once you start to slide, you undergo kinetic friction was even less, and you're going to really start sliding, and there's nothing you can do. You're just going to go straight off the road. Newton's first law of motion will take over, and you'll slide straight off the road. You won't go flying straight out, but you'll go that way. All right, so how fast would we actually have to go if we have conditions are wet? All right. So I'm going to erase this now. All right, let me take that out, simplify this a little bit. So we got mu g is comparing it to v squared over r, and the limit you can go, the limit of speed, all right, to keep going, to stay right on the road as a maximum is mu g equals v squared over r. So if we have a wet road, and we're going to using g is 10 meters per second squared for simplicity, and we're not worrying about sign of this because we're only comparing the size of numbers. This would be 0.6 times 10 equals v squared over r, which is 100. That would be 6. Multiply both sides by 100. That's 600 is v squared. Take the square root of that. V then is about 24 meters per second, which is, let's see, on the order of about 50, let's see, something on the order of, let's see, 48, 52 miles per hour. All right? That would be about it. Now let's take one last example of this. Let's say you have ice, right? You have ice on the road. In that case, mu static can be as small as 0.1. So if you had like freezing rain, ice, what would be the limit there? Same situation. The limit would be how fast you can go is when these two equal each other. So the only difference here would be that we have 0.1 times 10 is v squared over 100. So that's going to be 1 times 100 is v squared. So v would be 10 meters per second, which is roughly only about 22 miles per hour. So if it's icy on a curve like that, you could only go 22 miles an hour, right? Which is drastically less. Now, one thing also is if you realize you're going too fast coming into a turn, and it's really icy, and you are in the turn and just about to lose it, you can't, if you're going to try and brake, you have to brake it so you're maintaining contact roll. That's why anti-lock brakes, they stop so that you slide, rotate, wheel rotates, so So it's maintaining static friction. As soon as you start going into kinetic friction, that is less than static friction, so you're going to start sliding even worse. So that's why you want to maintain contact with the tires with the road, because you undergo static friction. If you have kinetic friction with ice, kinetic friction is on the order of 0.02 or less, and you're talking about speeds on slight to actually try and slow down again. You're talking about speeds on the order of 5 miles per hour. Well, that's kind of hopeless in that case. So you have to slow down before you get there. Static friction is always greater than kinetic friction. The limit is given by this expression, as far as the fastest you can go given the conditions, and you stay on the road as long as the frictional force is greater than centripetal acceleration. So that is all of chapter